D area. By the way, I have a really nice proof of the optimality of Huffman coding, but that would take about half an hour, and we've distilled it and refined it. It's in the text, so you'll do that. And I have outlined why it's true. I just haven't outlined, I haven't filled in enough of it to please a person who wants to call it a proof. Huffman coding theory. So let's look at this example. D equals 3. And we have 7, 6, 5, 5, 5. We want to code for that, and we have 3 branches in the tree from each node. So we combine these, and we get 15, we get 7, we get 6, and then we combine these, and we get 28. So the first question should be, is the object here, or is it here? That is, you get yes or no. Yes for this, or no for this, in which case it's yes for that. And then the next question should be which one it should be. So that's Huffman coding. But look what happens if the probabilities were this. 7, 6, 5, 5. Well, then we would combine these. We would get 16. We get 7. Uh-oh. The first question is inefficient. And the first question should be pretty efficient. We have combined these in a way that the first question only divides the set in 2. So we should add a dummy. And this becomes then 7, 6, 5, 5, 0. Now these combine into a 10, this into a 7, that into a 6, 23. The code words are, let's call them 0, 1, and 2. 0, 1, and 2. This code word is a 1. This code word is a 2. And this code word is 0, 0, 0, 1. And I don't care about that. So you add a dummy so that on the last question you have 3 forks. So you can write a formula for how many dummy zeros to add. Obviously you want either 3 masses, or you want 5 masses, or you want 7 masses, or so on, for that to be true. Now here's another example for D equals 4. 4-area Huffman code. D equals 4. And let's try this. 7, 6, 5, 5, 5. Well, after a little inspection, you can see that you should add 2 zeros and then combine these together to give you a total probability of 10. And then the 7 goes here, 6 goes here, 5 goes here, and then 2, 2. 17, 23, 28. Any questions about this? I've added some dummies so that my first question is useful. And you can write a formula for the number of dummies you need for a given alphabet size. By the way, the code words here are, we could call this 0, 1, and 2, and then call this one 3, 0, 3, 1, and then this would be 3, 2, and 3, 3, but these don't occur, so we don't care about those code words. And that would then be a set of code word lengths that satisfies Kraft's inequality with strict inequality. We're not using the full power here, but we're using it as best we can. Generally, by going to longer block lengths, the probability of 2 of these would be 7/28 times 7/28, et cetera, then you can get rid of the wastage. All right, great. Now, I just have one remark now to make, 3 remarks to make about Huffman coding. All right, for an optimal code, if P1 is greater than P2, greater than P sub m, then necessarily the code word length L1 less than L2 less than LM. Because otherwise we would just swap and minimize, cause summation of PILI to be less. Furthermore, for an optimal code, the last 2 code words are of the same length. Why? Because if there's a dangler, one that's longer, you just snip it off. You didn't need that extra symbol, that extra question. So swapping and trimming will prove that the L's are anti-ordered and that the last 2 L's are the same. And then finally you just need to say that there's an optimal code for which the code words here are some code word followed by a 0, this is in D equals 2, and followed by a 1 in this case, and then all that merging that I mentioned for the proof of optimality of Huffman coding will go through. And then you can show that an optimal code for this reduction can be expanded to an optimal code for the next stage of P until you get to the end, and then you've proved optimality for that. All right. So questions like this, of course, are put on the homework. Can you tell whether a code is a Huffman, an optimal code or not? It better have these properties. Otherwise it isn't. Okay, we have finished 2 lectures today, 2 lectures last time. There'll be no lectures next week. We meet again next Tuesday, at which time homework set 5 is due, which you should pick up here. And there'll be a midterm the following Thursday, the week after next. Here are the solutions to 4 for those who have earned it. Whew.